In this lecture, we're going to review some algebra essentials. We'll start by talking about the real number line. So, the real numbers can be graphically represented by the real number line. The real number associated with any point P is called the coordinate of P. So, the real number line is a horizontal line that represents all of the real numbers. Typically you'll see tick marks that represent all of the integers, such as -3, -2, -1, 0, 1, 2, and 3, and then we can add in the other numbers which we may need to deal with. For example, on this number line we've graphed -3/2 in between -2 and -3. We've plotted the point of square root of 2 in between 1 and 2, and pi lies just on the right-hand side of 3. Note that on the real number line, the negative numbers lie to the left of the origin, or the point 0, and positive numbers lie to the right of the origin. And the origin is represented by the coordinate of 0. So 0 is the coordinate of the origin. Notice that numbers to the left are smaller than numbers to the right. So, using the number line, we should be able to graph inequalities. If we look at this number line, we see that A is to the left of B, and so we can write the inequality A is less than B, because points that are to the left of the number line are smaller. On this number line, we see that A and B occur on the same point, and so we can conclude that A is equal to B. If two points lie at the same position of the number line, they have to be the same number, or equal to each other. And finally, on this number line, we see that A lies to the right of B, so we can conclude that A is greater than B, because numbers that fall to the right of the number line are larger than those to the left. So, using these concepts of the left being smaller numbers and the right being larger numbers, we can actually graph inequalities. Note that if you see that A is less than B, that's a strict inequality, and so when we graph it, we need to use an open circle or a parenthesis on the graph. And if we have A is less than or equal to B, that's called a non-strict inequality, so we'll use a closed circle or a square bracket on the graph to indicate that the points are included in the inequality. So let's do an example. We want to sketch the graph of the inequality x is less than 4. So we start with just a number line, and we need to find the point where 4 is on the number line. Okay, so we found 4 on the number line. We want to graph x is less than 4. So where are the numbers that are less than 4? Are they to the left or to the right? We want to draw a line in the direction that's less than 4. Additionally, since this is a strict inequality, 4 will not be included, so we need to use either an open circle or a parenthesis. Keeping all of that in mind, the sketch of the inequality x is less than 4 will look like this. We see an open parenthesis at the point 4, and we shade to the left of 4, showing that all of the numbers to the left of 4 are less than 4. Next, we're going to talk about finding the distance on a real number line. The absolute value of a number represents the distance on the number line from that number to the origin. Mathematically speaking, the absolute value is defined as follows. The absolute value of the number a is equal to itself if a is positive or 0, and the absolute value of a is equal to the opposite of a if a is less than 0. So, for example, we want to find the absolute value of 4. 4 is a positive number, so using the definition above, the absolute value of 4 would just be itself. So the absolute value of 4 is 4. For another example, if we want to find the absolute value of -3.2, -3.2 is a negative number, so using the definition above, the absolute value of -3.2 will be the opposite of -3.2, which is a positive 3.2. So the absolute value of a number is always going to be positive. Since absolute value represents the distance on the number line and distance is always positive, the absolute value will always be positive. Further, if P and Q are 2 points on the real number line with coordinates little a and little b respectively, the distance between those points, P and Q, denoted d of P, Q, is defined as follows. The distance between P and Q is equal to the absolute value of b minus a. So let's do an example. We want to find the distance between the points 1 and negative 1. So to find the distance between the points 1 and negative 1, we're going to want to plug 1 and negative 1 into the formula above. So that's going to give us the absolute value of negative 1 minus 1. If we simplify that, negative 1 minus 1 is negative 2, so we have the absolute value of negative 2. And the absolute value of negative 2 is just 2. So the distance between the points 1 and negative 1 on the number line is just 2. And that makes sense. If you draw out your number line and you count the distance between negative 1 and 1, you go from negative 1 to 0, that's one space, and then from 0 to 1, that's a second space. So the distance between them is equal to 2. Next, we want to talk about evaluating algebraic expressions. The field of algebra deals with variables such as x, y, a, b, pretty much any letter, to represent numbers. So to evaluate an algebraic expression, what we're going to do is we're going to substitute for each variable the numerical value that is given. So let's do an example. We want to evaluate the following expressions if we're told that x equals negative 2 and y equals 3. So first, we want to find out the value of 3x plus y, again, if x is equal to negative 2 and y is equal to 3. So to evaluate this expression, what we need to do is plug in the values that we know for our variables. So we plug negative 2 in for x, and we plug 3 in for y, and then we're going to simplify. Remember, from order of operations, we do multiplication first. And so 3 times negative 2 gives us a negative 6. So this is negative 6 plus 3. And then we can do the addition. Negative 6 plus 3 gives us a negative 3. And so the expression 3x plus y would equal negative 3, given that x is negative 2 and y is 3. Next, we want to evaluate x plus y divided by x minus y using the same substitutions. So we plug negative 2 in everywhere that we see an x, and we plug 3 in everywhere that we see a y. So that gives us negative 2 plus 3 divided by negative 2 minus 3. And to simplify this, we're going to evaluate the numerator and denominator separately. So in the numerator, we have negative 2 plus 3, that gives us 1, and the denominator is negative 2 minus 3, that gives us a negative 5. So this is 1 divided by negative 5, which can be rewritten as negative 1/5. So the answer for x plus y over x minus 2 is negative 1/5. Now we're going to talk briefly about the domain of a variable. The domain of a variable is defined to be the set of values that a variable may assume and produce a real number. So this is the set of numbers that you can actually plug into the expression and get an actual answer back. Now the two things that we're going to be concerned with when we find the domain is, remember, the denominator of a fraction cannot be 0, and the number underneath the square root sign cannot be negative. So these are what we're going to look at to find the domain. So, as an example, we want to find the domain for 4 divided by 2x minus 1. Well, remember, the denominator of the fraction can't be 0, so that's what we're going to use to find out what the domain can be. The domain will be all numbers as long as the denominator is not 0. So let's make a note of that. 2x minus 1 cannot equal 0. Let's solve this and find out what x would not be. We can add 1 to both sides of the equation, and then we have 2x cannot be equal to 1. Next, we divide both sides of the equation by 2, and we see that x cannot equal 1/2. So the domain is going to be the set x such that x cannot equal 1/2. So all values of x except for 1/2 would give us a number when we plug them in. Now let's talk about some laws of exponents. To begin with, the exponential expression a raised to the n power, where a is called the base and n is the exponent, is defined as follows. A to the n power is equal to A times A times A times A, where A appears n times. If the base A is not equal to 0, then anytime you have A raised to the 0 power, that will always be 1. So any base raised to the 0 power will be 1. And if the base A is not equal to 0 and the exponent n is positive, then A to the negative n is going to equal 1 over A to the n power. So this says that if you have a negative exponent, you can rewrite it by taking the whole exponential expression and putting it in the denominator with a positive n value. Let's look at a couple of examples where we deal with negative exponents. First, we want to evaluate 2 raised to the negative 4 power. Well, remember, for a negative exponent, you can rewrite the exponential problem by taking the base and exponent and putting it in the denominator, and that'll make the exponent positive. So 2 to the negative 4 power can be rewritten as 1 divided by 2 to the positive 4. And then we can evaluate 2 to the positive 4 is just 16, so 2 to the negative 4th power will be 1 over 16. Now let's look at x to the negative 3 power. Again, since the exponent is negative, we can rewrite it by moving the exponential problem down into the denominator, so x to the minus 3 can be rewritten as 1 over x to the third. Here are a few laws of exponents which we're going to use throughout this course. First, if you have a to the m times a to the n, so two exponential functions with the same base but different exponents, you can multiply them together by keeping the same base a and adding your exponents together. So a to the m times a to the n equals a to the m plus n. Second, if you have an exponential expression a to the m that's further raised to another power n, so a to the m raised to the n power, you can simplify that by multiplying the powers together. So that would be a to the m times n. Third, if you have a product a times b and the entire product is raised to a power n, you can distribute the exponent to both terms, so ab to the n power is going to equal a to the n power times b to the n power. Fourth, if you have a to the n divided by a to the m, so a quotient of two exponential expressions that have the same base but different exponents, you can combine them together using the same base and subtracting the exponent of the numerator minus the exponent of the denominator. So a to the n divided by a to the m equals a to the n minus m, again assuming if a is not equal to 0. And finally, if you have the quotient of two numbers a divided by b and the entire quotient is raised to the nth power, you can distribute the exponent n to both the numerator and denominator. So a over b to the n equals a to the n over b to the n, assuming that b is not equal to 0. Let's do some examples. We're going to use the laws of exponents to simplify the following expressions, and we want to make sure that we write our answers so that there are only positive exponents. So anytime we see a negative exponent, we need to move it to the denominator. So to begin with, we want to simplify x to the negative 1 times y, all raised to the third power. We'll start by using the third law on the previous slide that says if you have a product raised to a power, you can distribute the power. So we can rewrite this problem as x to the negative 1 to the third power times y to the third power. Next, we'll use the second law from the previous slide that says that if you have an exponential expression raised to a power, you can simplify that by multiplying the exponents together. So we had x to the negative 1 raised to the third power. We can rewrite that as x to the negative 1 times 3. We simplify by multiplying. Negative 1 times 3 is negative 3, so now we have x to the negative 3 times y cubed. But remember, we don't want to have negative exponents, so we need to rewrite x to the negative 3. And so to rewrite x to the negative 3, we will move the exponential expression into the denominator, so we can rewrite that as 1 over x cubed. So we have 1 over x to the third times y to the third. And the final step is just to combine things, so 1 over x cubed times y cubed is going to give us y cubed over x cubed. And so that will be the simplification of the expression we were given. Next, we want to simplify the expression 4 times x to the negative 2 times y to the negative 1 times z to the negative 1, all divided by 2 cubed times x to the 4th times y. We'll start just by simplifying 2 cubed. 2 cubed is 8, so we're going to have an 8 in the denominator, 8x to the 4th times y. Next, we want to simplify things variable by variable. So if we start with our constants, 4 divided by 8 can be rewritten as 1/2. If we look at x to the negative 2 divided by x to the 4th, remember we can combine the quotient of two exponential expressions by subtracting their exponents. So that would be x to the negative 2 minus 4. Similarly, y to the negative 1 divided by y can be y to the negative 1 minus 1. And then z to the negative 1, since that's the only z we have, it'll stay by itself. Next, we'll go ahead and simplify those exponents. So 1/2 stays the same. X to the negative 2 minus 4 will become x to the negative 6. And y to the negative 1 minus 1 becomes y to the negative 2. So this is going to be our answer, but we have negative exponents that we need to take care of. So what we'll do is we'll move all of those expressions with negative exponents into the denominator to make them positive. And so the answer is going to be 1 divided by 2 times x to the 6th times y squared times z. Next, we're going to talk about evaluating square roots. By definition, if a is a non-negative real number, the non-negative number b, such that b squared is equal to a, is called the principal square root of a. And we write that b equals the square root of a. So let's look at a couple of examples. First, we want to figure out what is the square root of 9. So what non-negative number squared would give us 9? And of course, that's going to be 3. Since 3 squared is 9, 3 is the square root of 9. Next, let's look at the square root of 1 divided by 64. So to look at this, we can consider the numerator and denominator separately. What number squared would give us 1, and what number squared would give us 64? And again, that would give us 1 over 8, since 1 squared is 1 and 8 squared is 64. So the square root of 1 over 64 is 1 over 8. Finally, we want to evaluate the square root of 1.3 quantity squared. Now, this one is actually pretty easy because when you have the square root sign and the square sign together, they cancel each other out. So the square root of 1.3 squared is just going to be 1.3. And so in general, if you have the square root of some number squared, that's just going to be the absolute value of that number. For example, the square root of 4 squared will equal the absolute value of 4, which is just 4. The square root of negative 5.7 squared will equal the absolute value of negative 5.7, which is just 5.7. For our last topic in this section, we want to talk about scientific notation. So when a number has been written as the product of a number x, where x is between 1 and 10, times a power of 10, that's called scientific notation. And so we want to be able to convert from a decimal to scientific notation, and vice versa, from scientific notation to a decimal. So let's talk about converting a decimal to scientific notation. The first thing that you're going to want to do is count the number of places that the decimal would have to be moved to arrive at a number x that is between 1 and 10. Alright, if your original number, the number that you started with, is bigger than or equal to 1, then your scientific notation would be written x, which was that number that you got in step 1, times 10 raised to the nth power, where n is the number of places that the decimal would have been moved. And then if the original number is less than 1, the scientific notation would be x, again where x is the number that you found in the first step, times 10 to the negative n, where n is the number of places the decimal would have to be moved. So let's do a couple of examples that deal with scientific notation. First, we want to write the following numbers in scientific notation. The first number that we want to look at is 21,210. So we need to figure out how many spaces would we have to move the decimal point that would occur after the 0 in order to get a number that's between 1 and 10. And so if we look at this, we would have to move that decimal place 4 spots to the left to get 2.121. And so the n value in our scientific notation would be 4, and the x value would be 2.121. And since 21,210 is bigger than 1, we would write this in the form 2.121 times 10 to the 4th power. For our second example, we want to look at the number 0.0514. So again, how many places would we have to move the decimal to get a number that's between 1 and 10? And it looks like we would have to move the decimal 2 places to the right to get the number 5.14. So when we go to our scientific notation, the x value will be 5.14 and the n value will be 2. And since our original number 0.0514 is less than 1, we would write this as 5.14 times 10 to the negative 2. And for our last example, we want to write the following number as a decimal: 9.88 times 10 to the negative 4th power. Now, since we have times 10 to the negative 4th power, we know that the number we're looking for is going to be less than 1. So what we can do, we can take the decimal place and move it 4 spaces to the left. So in general, when you have a number in scientific notation, if the power is negative, move your decimal point to the left. If it's positive, move it to the right. So we're going to move 4 places to the left, which will result in 0.000988. And so that will be the decimal that we're looking for, 0.000988.